Okay. Yeah. Today, we start with the chapter 4, which is the determinant. Determinant start from the definition and property of determinant and cofactor expansions and applications and Cramer's rules and the application of determinant. And eigenvalues and eigenvectors. Today we will cover the section 4.1. Okay. The concept of determinant was introduced far earlier than the concept of matrix. It was used to solve the system of linear equations more than 100 years, even before the concept of matrix. In the late 19th century, Sylvester introduced the concept of matrix and method of solving system of equations by using an inverse matrix. Okay. In this chapter, we first define the determinant and we'll see the properties of determinant. Then we study how to compute the determinant from the definition and by using the elementary operations and by using the cofactor expansion. And then we will define the most important concept in linear algebra, which is eigenvalues and eigenvectors. Okay. And Arthur Cayley was one of the important figures who on the study of matrix algebra. And John von Neumann was the one who used this linear algebraic concept and algorithms to give a life to the computers. Section 4.1, the definition of determinant. Okay, here we introduce a determinant function which assigns any square matrix to a real number, f of a. Okay. In order to define the determinant function, we first introduce permutation. Then we will study the properties of a determinant function. Permutation. For a set of natural numbers from 1 to n, a permutation is a one-to-one function from S to S. one-to-one function. 의미하는 바가 뭐냐면 이 1부터 n까지로 보내는 1대1 대응 함수 된 소리예요. 그러니까 1을 2로 보내고 뭐 2를 5로 보내고 n을 1로 보내고 하는 식으로. 결국은 이거는 이쪽 이미지는 1부터 n까지가 재배열된 셈이 되겠죠. So this sigma is the permutation is a function from S to S, bijective function, one-to-one correspondence function. We simply denote the permutation as sigma. Suppose we have this function, this permutation function, then this, since these 1 to n's are fixed, so we can write this function as this. Like 1 goes to sigma 1, 2 goes to sigma 2, and n goes to sigma n like this. Or since this is a rearrangement of the number from 1 to n, so we can just write the numbers in order. I1, I2, and In. 1 goes to I1, 2 goes to I2, n goes to In like this. So this is a kind of function. And the representation of the function. As a permutation sigma is a one-to-one correspondence, the range is simply a rearrangement of 1 through n, just rearrangement of those numbers. Hence, there are n factorial permutations on S. So we have n factorial permutations on S. because if we're fixing the position of first element, then leaves n minus 1 factorial possibilities to commute the last. Okay. We denote set of all permutations of set S by Sn. Then the cardinality of Sn is going to be n factorial. Its elements are all each permutations. Okay. Think about S1 when n is equal to 1. S1, we have only one permutation that sends 1 to 1. There's only one. So for n, when n is equal to 2, and S2 has two functions, two permutations that sends 1 to 1 and 2 to 2. That's the one permutation. The other one is send 1 to 2 and send 2 to 1. There's only two permutations. For 3, we have 6 permutations. So that sends 1 to 1, 2 to 2, 3 to 3, and 1 to 2, 2 to 3, 3 to 1, etc. And send 1 to 3, and 2 to 2, and 1 to 1. So we have 6, which is 3 factorial. For 4, we have 4 factorials, number of permutations. Okay, because this is a whole the whole rearrangement of numbers from 1 to 4. So these are the all permutation, the functions. Next, we define inversion. In permutation, J1 to Jn, this permutation, on inversion, is the case when a bigger natural number placed on the left-hand side of a smaller natural number. Okay, for example, in this permutation, 1, 4, 2, 3, for example, this 4 is placed in front of the smaller number 2. So this 4 has an inversion. And 3 is also, the 4 is ahead of the smaller number 3. So this 4 also has the inversion with the 3. Okay? So this 4 has what? There is 1 inversion and 2 inversion. This one has 2 inversions. Next, what about? Okay, so this permutation has 1 inversion for 2 and another inversion for 3. So it has 2 inversions. Okay, so we can now define a number of inversion for one number. So one number in permutation. Okay, that is after k plus 1th index, the number of indexes which is smaller than k's index jk is called the number of inversions for jk. So in this case, 4 has 2 inversions, so the number of inversions for k is 1 and 2, so it's like 2 inversions. Okay, so the number of inversions for whole permutation, the one permutation, one whole permutation of these is the total number of each number of inversions for from J1 to Jn. 그러니까 하나의 퍼뮤테이션이 있으면 퍼뮤테이션의 각각의 숫자들이 있죠. 1부터 n까지. 그 각각의 각각의 숫자가 넘버 오브 인버전을 갖죠. 그것들을 다 합친 것이 그 퍼뮤테이션의 인버전 숫자가 되는 거예요. Okay? So the number of inversion for a permutation is the addition of inversion number for each of these J1 through Jn. Okay? Okay, next. If a number of inversion for permutation is even, since it's a number, so number can be even or odd. So the total number of inversions for a permutation is even, then we call it is an even permutation. If the number is odd, then we call that permutation is an odd permutation. Okay. Any questions? Okay, so first example asks us to determine whether the permutation is even or odd by computing the inversion number for permutation. the sigma, in S5. Okay, the set from 1 to 5. Okay. This is one permutation that sends 1 to 5 and 2 to 1, 3 to 2, 4 to 4, and 3 to 3. Okay? So how many inversions this number 5 has? 5 has 4 smaller numbers on right. So the inversion has 1, 2, 3, 4. It has four inversions. 5 has 4 inversions. What about 1? There's no smaller number on right of 1. So there's no, the inversion number for 1 is 0. What about 2? There's no smaller number on right of 2. So the inversion number for 2 is 0. 4. 4 has 1 smaller number, 3, on right. So the inversion number for 5 is, for 4 is 1. For 3, there's no number. There's no smaller number on right. So the inversion number for 3 is 0. Mm-hmm. Mm-hmm. Okay, so what's the total number of inversions? 4 plus 0 plus 0 plus 1 plus 0. So what is it? 5. So we have 5 inversions in this permutation function. So what is so this is an odd number of inversions. So this is going to be an odd permutations. Okay, that's the way. Mm-hmm. You can define a permutation like this and ask the number of inversions with this command. Then it shows you the inversions, and the number of the inversions is going to be 5, like what you found here. So if you have a permutation, the number of inversions and the shape of inversions can be found like this. So this, if you ask whether the given permutation 5, 1, 2, 4, 3 is even, then it says no, it's not uneven permutations. If you ask it odd, then it will give you yes, true. Mm-hmm. Next, we define a signature function. Signature function is a function defined on Sn, set of all permutations on S. Mm-hmm. This codomain is 1 or minus 1, only 2 numbers. Okay. Which assigns each permutation of Sn to either +1 or -1. If sigma is an even permutation, then signature of sigma is +1. If sigma is an odd permutation, then signature of sigma is going to be -1. Okay? Okay. So when we have a permutation, then we can figure out whether it is an even or odd permutation, and then we can find the value of signature of that particular permutation among n factorial permutations on S. Okay, then let's classify the permutations of Sn to either even or odd permutation. Okay, for S3, how many permutations do we have? S3, 3 factorial. So we have 6 permutations like this. Okay, this has this permutation send 1 to 1, 2 to 2, 3 to 3, and as you see, there's no inversions. It's in the order, in the increasing order. So there's no inversion. For this, how many inversions? We have 2, the 3 is ahead of 1, and 2 is ahead of 1. So we have two inversions. Bigger number is in front of smaller one, so it occurs an inversion. So we have 2 inversions. What about this? 1, 3, 2. You have 3 is ahead of 2. So we have 1 inversion. It's odd. 3, 2, 1. Here we have 3, 2 has an inversion, and 3, 1 has an inversion, and 2, 1, this one also has an inversion. So we have 3 inversions. Important thing is this 3 has 0, 2, 2 inversions, which are even. So we have 3 even permutations among the permutations on S3. And we have 3 odd permutations, 1, 1, 3, among the 6 permutations on S. Okay, 1, 2, exactly. Okay, so the important thing is we have 3. So the signature value of each permutations are +1 and these are -1s. Important thing is among 6, half was uneven permutation and half was the odd permutations. So this actually is true for general n. So suppose you have a n, for the Sn, you have n factorial permutations. Then half of those are even permutations, and another half of those permutations will be even permutations, half and half. In permutation, if 2 numbers switch the location, then the signature is changed. If 2 numbers switch in one permutation, then the number of inversion occurred. Number of inversion. Okay, whether it's small or larger, and the number of inversions occurs always the odd numbers. Okay, if you okay, so next, the number of inversion will be added by odd numbers. If it was it's attached, if you rotate it, then only one more inversion are added or less, or subtracted. Okay. If it's far away, then also you will find the pair of the permutation changes. So anyway, so if you switch the location of 2 numbers in one permutation, then signature is changed. This gives this theorem. Let tau be a permutation by switching any 2 numbers from a given permutation sigma, then signature of tau is equal to minus signature of sigma, the original one. Okay. With those concepts, permutation and signatures, we define a determinant. This is called the Leibniz formula. Let A be a n by n matrix. Then we denote the determinant of matrix of A, determinant of matrix A, with this. We call this as, we can write this as a determinant of A or a bar of A, like this. These are the notations. What this means? This means you choose only one entries from each rows without redundant. So you just choose one element from each row without the what? 이렇게 겹치지 않게. Okay, without duplications. And then multiply all those n terms. Then multiply +1 or -1, depend on those permutation functions that you choose. Then add all of those. How many? N factorials. Because the sigma comes from Sn, whose cardinality is n factorial. Okay? Okay, this is the ideal definition of determinant. Choose one entry from each rows, then multiply. Then you have n factorial of those product of n terms. And then give a half plus signs for even permutations, give a minus sign for half among n factorials, then add all them to make a determinant. Okay? So for 1 by 1 matrix, you have only one permutation, which stands 1 to 1. So if A is a 1 by 1 matrix like this, then you have just A as a determinant. If you have a 2 by 2 matrix like this, then you have 2 permutations, sigma 1 and sigma 2, like this. Okay? And as you see, the signature of sigma 1 is 1, signature of sigma 2 is -1. This is an even permutation, this is an odd permutation. Then determinant A is defined with the product of these two times the signature of sigma 1, product of A1 sigma 2 of 1 times A2 sigma 2 of 2 times the signature of sigma 2 that we did use. Okay. Here, this sigma 1 of 1 send 1 here, so A1 1. 2 goes to 2, so A2 2 here. And this is even permutation, so we multiply plus 1. Here, A1 sigma 2 is send 1 goes 2, so A1 2, and 2 goes to 1, so A2 1 here. So we have this with the odd permutation, which we multiply negative 1 and add all them. That's it. Actually, this can be found in this way. If you have 2 by 2 matrix, then A11 times A22 plus, and A12 times A21 times minus 1, and add this here. And this is called the Serres method for 2 by 2 matrix. As you see here, each terms of this in the determinant is from the matrix of A by choosing a row and a column and without any overlapping. Then multiplying them and assigning a corresponding signature. Okay. Choose one from each row and column without any overlapping and multiply product, all of them, then multiply the sign, that corresponding signature, the corresponding permutations. This is it for the 2 by 2 case. What about 3 by 3 matrix? For us, if it's a 3 by 3 matrix, we have how many permutations on S? 3 factorial. 6. We have this 6 factorial, as you saw. That's that? Okay, then what's the determinant? We have S3 like this, and we know the first 3 are even permutations, and the last 3 are odd permutations. So corresponding signatures are like this. By substituting them into the definition of the determinant, then we have what? We have first one times signature of sigma. For the second permutation, we have this. And 3, 4, 5, 6, we have this. Okay. Then what will be this? First one. These 3 are plus and these are minus. And A, this 1 goes to 1 and 2 goes to 2. 3 goes to 3. So A11, A22, A33 3 for the first one. Second, 1 goes to 2, so A12, 2 goes to 3, so A23, and 3 goes to 1, so A31, like this. And so on. For example, for this one, 1 goes to 3, so A13, 2 goes to 2, A22, 3 goes to 1, so A31, with the negative sign, because this was an odd permutation. So we have 3 terms from 3 even permutations and 3 terms from the 3 odd permutations. These 6 terms can be found in this way. If we have a 3 by 3 matrix like this, then we add this on the left and this third column to the left, and this first row to the right. Then you will see there are what 3 terms on this direction and 3 terms on these directions like this. Then, as you see here, this A11, A22 to A33 plus A12, A23, and A31, and A13, A21, A32. We have 3 terms here, and you have a product of these 3 entries, which gives you A12, A21, A33, A13, A22 to A31, and so we have 3 terms with the minus signs because it corresponds to the odd permutations. Okay, so from here we have 3 terms from here and negative 3 terms from here, so we have 6 terms. So Serres found this way, easy way to find the determinant of 2 by 2 and 3 by 3 matrix. Okay, but actually that does not work for the larger size matrices. It only work for these 2 by 2 and 3 by 3s. That's method. Okay, and next example, compute the determinant of the following matrices. Two matrices. For 2 by 2 matrix, and 3 times minus 2 is here, and minus times 1 times 4 here, gives us minus 10. For 3 by 3 matrix, and you found 1, 5, 9, and 2, 6, 7, and 3 minus 4 minus 8. That gives you these 3 terms. And here 2 minus 4, 9, and 3, 5, 7, and 1, 6 minus 8 gives you this with all minus signs multiplied. Then it gives you 240. Okay, so you now know how to find the determinant of it by using the Serres method for 3 by 3 matrix, or by the definition of determinant. And also, if you define a matrix, 3 by 3 matrix like this, then find the determinant of B. Of this command gives you the determinant which was that we found. So we can actually compute the determinant with these algorithms. Here, the remark: so Serres methods cannot be applied to the case of degree 4 or higher, because on those way, for 4 by 4 matrix, even if you expand it, you cannot have 12 straight lines, and another 12 negative lines from those figures. So actually, it's impossible for the larger size matrix. It's impossible. So we should find a better way and general way to calculate the determinant of the given matrix of large size. So we have to study the property of determinant to help us to compute the determinant. Okay? So here, first property of determinant that we found was a square matrix A and its transpose has the same determinant. Determinant of A is same as determinant of A transpose. As you see here, if determinant of B is 240, like what you saw, then B transpose is this matrix. If you find the determinant of B transpose, you will have the same value. Actually, it's all work for any matrix. Okay. The proof of this comes from the definition. For the transpose, when you have a transpose, the inversion occurs evenly. If this goes to here, and so the number of the inversions occurs and for every permutations and evenly. So the sign basically does not change. So the values are always the determinant values are always the same. So here for B matrix, you found the transpose of B and determinant of it, then you will have the same values. If you randomly generate it, it also will work. Okay. And the property, so this gives you the property of determinant regarding the rows also work for columns. So if you find any property of determinant for rows, then same work for the columns. Here is the main theorem that you should know. Let B be a matrix obtained by switching 2 rows or columns from a square matrix A. Okay? If you have a matrix A, then you find two rows and switch those 2 rows. Then matrix B. And the determinant of that matrix is minus 1 times the determinant of the original matrix. Okay. This is very important property that will be used over and over again. Next. Okay, I will start with this explanation first. In order to show this, suppose 2 adjacent rows are interchanged. If you switch the 2 rows, first 2 rows, or 2 adjacent rows, then any reversals in terms would not be affected except for the reversal of the element of that term within that 2 rows. in which case adds or subtract a reversal, thus changing the signs of all terms and thus the signs of the matrix. Okay. So if you change the two adjacent the rows done, then the sign changes occurs by add or subtract or reversals. With those in mind, we expand this to a general two rows. Suppose we interchange the R slow and S slow. R slow, not these two, and J slow, which the S is R plus K slows. S is the R plus slow. Okay, then this interchanges successively the R slow to R plus first row. First, R rows goes to the small R rows goes to R plus 1 slow. So we made one interchange. Then you do it once again to R plus 1 to R plus 2 slow. And if you do it K times, then you will have this R slow on the S position, S slow positions. So then the R plus first 1 slow and the R plus second 2 slow, and then it's continue in this fashion until one reaches R plus K minus 1 slow. Okay, do it over and over again until this first slows goes to R plus K minus 1 slow. Then actually the R slow went to the S slow. Then S slow moved up to S minus 1 slow. Okay. Then from there you do interchange the S minus 1 slow to the above, and then once again until it reaches to the R slow. Then we go back until one goes back to the R slow. Okay. Then you are done. Then just count out how many times you switch it, rows, when you move R slow to S slow and S slow to the R slow. This has the same effect as switching the R slow and the S slow. Okay? The other rows stays at the same place because you went forward and backward once again. It takes R minus 1 switch for going forward. When you moved R to S, you did K minus 1 switch and K minus 2 switch for going backward. When you moved the S minus 1 slow to R slow after this. So their sum must then be an odd number. So when you switch it R slow and S slow, then you have eventually odd number of row change, which means signature of the signature change should be the product of this odd number of times minus 1 times minus 1 times minus 1 at the odd numbers. Okay, so the total effect is to multiply minus 1 because if the original permutation was the even permutation, it's going to be a odd permutation and vice versa. So this comes from the theorem 4.1.1. If you switch one, then one sign change was made. Now you have the even number of sign changes, so you have just one sign changes. Okay, with those in mind, it can be proved easily. Let B be a matrix obtained by replacing R's and S's law of A. Assume R is strictly less than S. Then all the entries of B are same except R's law and S's law. R's law of A, B is actually S's law of A, and S's law of B is R's law of A because we switch it. think about the determinant of B. From the definition, we have this summation sigma and sine of sigma times B1 sigma times B R sigma R and B B S sigma S B N sigma 1. This is the definition of determinant. Okay? Okay, then, since we have all the terms are same, Bi's and A's, except these two rows. So everything's the same except these two terms, this one and these terms. B R sigma of R is actually B S sigma of S, and B S sigma of S is S A R sigma of S, because two rows were changed. So this number should be this one. Okay, then, so this is basically this and this is the same matrix. So this is in terms of B and in terms of A. Here we just switch these two numbers. This one goes to here. This one goes to here. This does not make any changes, because this is the product of scalar numbers and terms. Among those two, you just changed it. You didn't do anything on permutation. This is just a switch of two numbers. Nothing happened. So this is rewriting. But see here, this is the permutation here is not in order. So we wanna rewrite it with this order. A1 sigma 1 times A2 sigma 2 AR sigma of R times AS sigma of S AN sigma of Y. We want to like it. Then what's the difference between these two permutations? Here, as we observed here, when we switched two rows, the number of inversions was made by odd number of times. So the signature was changed by just multiplying -1. So this can be written in this way by theorem 1.1, because we had 2k minus 3 times of the sign changes, which is odd number, when R is strictly less than S, and the difference was k. Okay, so this is the definition of determinant of A. So the determinant of B can be written as a minus determinant of A. That's it. Okay, with those in mind, check those properties. Suppose we have A and B, then determinant of A is 7. But if we switch two rows, then the determinant is going to be the minus of the determinant of original one. It can be easily checked. Next. If a square matrix has two identical rows or columns, then determinant of A is equal to 0, always. Why? 김영생-군? Why? Because you switch, if you have two identical rows, then when you switch it, let's say it's a matrix B, then the sign should be changed on the determinant. But if the two rows are identical, then basically these two matrices are same. So this matrix determinant should be same. Okay? So this equality should hold, which means 2 times determinant of A is equal to 0, which means determinant of A should be 0. So from the property that we just showed, this follows. Like you see, if we have two identical rows like this, then if you do find the determinant, it always will be 0. You can check it easily for any matrix, because two rows are same. A square matrix A has a row or a column with identical zeros. Then what? Determinant should be 0. Why? From the definition, you did choose one entries from each row and column without repetition, without overlapping. So if you have a 0 row, one of these terms should be always 0. So the product of those should be 0. So you have n factorial terms of zeros with different signs. So addition or subtraction of all zero should be 0. So determinant should be 0. Like this. If you have 0 rows, you in every 6 terms, you will see zeros in it. Isn't it? If it's a 5 by 5 matrix, then each 5 factorial terms will have zeros on each. So product of all those will be 0. So addition of all those zeros will be 0. Let B be a matrix obtained by multiplying k times the row of a square matrix A. Then determinant of B is same as just k times determinant of B. Why? From the definition of determinant, here this B matrix will have the same form, but only difference is one of these terms from that column, that row, will be k times A times I sigma of I. So this k, so all n factorial term will have k's in front. So we'll factor it out. Then this the determinant of that matrix will be just k times of this. So determinant of B will be k times determinant of A. If a row of matrix A is a k multiple of the original matrix A. This all comes from the definition. So example like this. If this 1, 2, 3 is here, if 2A6 is here, it's 2 times of this. So if you, you can factor it out, this 2, to make it 1, 4, 3. Then this 1, and also, it works on also for the columns. You have all 3's here. You can factor it out 3 here on the columns as well. Okay? Columns here, and factors out the here and 3's, like this. 2 from here and 3 from here, like this. Then you have what? You have 2 matrices whose columns are same. So what's the determinant of this? It's 0. So eventually the determinant will be 0, like this. So determinant, if you use those properties, then you can find the value of determinant easily. Next. If a square matrix has 2 proportional rows, then determinant of the matrix is always 0. Why? From this. If one row is proportional of the others, okay? If one row is proportional of others, like this, then you can factor that multiple outside. Then you have 2 identical rows. So determinant of that matrix is 0. So 0 times that k multiple is always 0. That's okay, so it comes from the earlier 2 theorems. Next, this. Third type elementary row operation and determinant. If you do the third type elementary matrix operation on A, which means k times of one row, and add it to the another row of A, then determinant should be same. So if you do the third type elementary row operation on a matrix, there's no change on determinant. This is very important. So you can, when you find the determinant, you can do the third type elementary row operation over and over again until you have a very simple form. But there's no change on determinant. Okay? Here is the proof. Without loss of generality, let B be a new matrix whose second row is obtained by adding k times of the first row of A to A. Okay? So the B matrix, you have an A matrix, you multiply k times on the first row and add it to the second row. Then what's the determinant of B? So from the definition of determinant, everything comes from A's, but second row, you have this instead of just A 2 sigma of 2. You have this because you added the first row to the k times the first row to here. We can rewrite this because all these are scalar. We can rewrite as this times k plus and this part. You can split it to 2 and you can factor it out k like this. Important thing is, what about this? This is a matrix. This comes from a matrix whose first row and second rows are same. because you multiply k times the first row on the second. This determinant comes from that matrix. So first part is have two same rows. So what's the determinant value? 0. So k times 0 is the value of this first part. And what's left? This. What is this? This is a determinant of A. This is determinant of A. You see? Because the first row and second row of this matrix is same. So determinant of A is exactly same as determinant of A, which is this. So third type operation does not affect on the determinant. As you see here, if A is a matrix, then 2 times of second row is added to the first row, and then this will be that matrix. Okay. 2 times of second row and add it to the first row. Then you will have this matrix. Then what is this? Then find the determinant. Then you will see the determinant will be exactly same as before. Okay. Next, determinant of triangular matrix. If it is an n by n matrix of triangular, then what's the determinant? Only the product of main diagonals. You don't need to think about all the off-diagonal entries, because you are choosing the element from each row and column without overlappings. So for the diagonal entries, yeah, you can find it and multiply it. And signature is +1. So you have this. What about other terms? Other n factorial minus 1 terms. When you choose the entries from each rows and column without overlapping, except this main diagonal, you have to choose some zeros from here when you choose n terms to product, to multiply. So every other n minus 1 term has minus 0 in it, so its product of them are all zeros. So all the rest of terms are zeros. So for if you have a diagonal matrix, it's easy. So if you have a matrix and do the elementary row operation, third type elementary row operation, and you have a RREF to REF, then determinant of the triangular matrix can be easily found, and that's the same as the determinant of the original matrix. That's the key idea. So suppose this is then the determinant is just multiply these main diagonal entries. That's it for triangular matrix. So REF is a very good one to find the determinant. So this is how to find the determinant. For a given matrix, do the elementary row operations to make many zeros in a certain rows or columns, and then make it REF forms, and multiply the diagonal element. That will give you. The only thing that you should keep in mind is during this elementary row operation, when you multiply k times a row or column, or switch the 2 rows or column, then do not forget multiply 1 over k or minus 1. Okay? When you multiply it, then you have to subtract it. When you switch it, then you should just have a sign changes. For it like this. When you find the determinant of this, instead of the Seller's method, you can do just rotate these 2 rows, and that gives you should use the minus signs here. Then you do multiply 2 and on the first row to make this one 0, which gives you this one. This is third type elementary operation, does not make any changes. Next, multiply minus 10 here to make this one 0, like this. It's third type elementary operation. There's no change on the determinant. Then what is this? This is a triangular matrix. So determinant of this is 1 times 1 times minus 55. Okay, so minus 3 times minus 55 is the determinant of the original matrix, like that. You can subtract minus 5 earlier before, but you can get it from here right away. Okay, let E be an elementary matrix. Then determinant of EA is same as determinant of E times determinant of A. As you see, here, when E is obtained by multiplying K, then what's the difference? Determinant of a matrix, identity matrix with one entry k, then determinant is just the product of diagonal entries, which is k. If you the elementary matrix is obtained by switching two rows, then it's not a diagonal matrix. Only two ones are in the upper diagonal at each position. Then determinant of that will be always -1 because one permutation from identity matrix. When you obtain E is obtained by multiplying k times a row, adding to it another row, then what's the determinant? That's still a diagonal matrix with all diagonal entries 1, and there's only one off diagonal entry which is not, which is k. So there's a triangular matrix. What's the determinant? That's 1, because it's a triangular matrix. So in any case, the determinant of EA is equal to determinant of E times determinant of A for every elementary matrices. Type 1 to 3. Okay, here is the equivalent condition for the invertible matrix. If A is invertible, if and only if determinant of A is not 0. Because if determinant of A is not 0, then you have a diagonal triangular matrix whose main diagonal entries are not 0. Okay, by RREF, by this elementary operation, and then it can be simplified to identity matrix. If determinant is not 0, then A can be simplified to the RREF of E's identity matrix, so it's invertible. With those, for any two matrix, AB and determinant of AB is equal to determinant of A times determinant of B, always. Okay, so this is important. This comes from this, actually, with the LU decomposition. Verify the above theorem, the AB. So if you find the AB and determinant of A and determinant of B is this, and determinant of AB is -10, and determinant of A times determinant of B is also -10, -255. It's always work. For a square matrix A is invertible matrix, and if determinant of A is not 0, then the inverse of determinant of A inverse is always a reciprocal of determinant of A. See, if it is a matrix and A inverse is this, and determinant of A inverse is just 1 over -2, like this. It's always work. I think that's the end of this section. Here you will see the code for the older examples in section 4.1 from example 5 to 15. For example, this is a matrix, then the determinant can be found easily. If you change the numbers, then you will have the determinant without any difficulties for any size. Transpose and the what? When you find the determinant whose determinant is equal to 0, then you see this is the matrix whose determinant is 0 is non-invertible. Okay, and if you find the determinant of AB and the determinant of A times determinant of B, you will find that they are always same for any matrix of any size. And if you find the determinant of A and determinant of A inverse, then they will be reciprocal for any arbitrary matrices. If you change the matrix, still it will be same. Like this. And I think that's the end of it, of the section 4.1. We had a big conference for linear algebra earlier, and here most of the specialists, more than 500 linear algebra specialists in the whole world, were gathered at Seongyungan University, and I think these are most of the research mathematicians in linear algebra were here. So yeah, it will be an interesting images that you like to see. Okay, next we will continue the section 4.2. Any questions?